Jai Shree Ram. Welcome to a new chapter of Civil Engineering Infrastructure (CEI). I am Rahul Pandey, and today we bring to you Highway Construction Process Part 2. In this video, we will understand the three most critical layers of road construction: Subgrade, GSB, Granular Sub Base, and WMM, Wet Mix Macadam. These three layers together form the true foundation of any highway. Each layer has its specific purpose, defined testing requirements, and clearly prescribed standards to ensure long-term quality. Civil Engineering Infrastructure (CEI) is a platform that connects site experience with textbook knowledge, so that construction is understood not just as work, but as engineering responsibility. So let us begin this journey. From subgrade to WMM, the layers that give life and strength to every highway. Recap of Part 1. Before moving ahead, let us briefly recall what we learned in Part 1, so that today's topic becomes even clearer. In the previous part, we understood where a road truly begins. Every project's real foundation starts with site preparation and earthwork. We learned that clearing and grubbing, topsoil removal, cutting and filling are not merely initial activities. The overall quality of the highway structure depends on them. During embankment formation, the selection of suitable boro material and its layer-wise compaction becomes the first promise of road durability. Each layer's field testing, its approval, and proper moisture control prove that construction is not just execution. It is responsibility and discipline. The spirit of construction. Every road tells a story. Every road carries a responsibility. This responsibility belongs to the engineer, who stands on site in heat, rain, and dust, and transforms soil into a road. The true essence of construction is understood when subgrade becomes strength, GSB provides support, and WMM becomes the soul of the pavement. Every layer and every process hides engineering science within it. Designed as per MoRTH, IRC, and IS specifications, construction is not just work. It is a process of trust, where every measurement, every level, and every test teaches a new lesson every day. This is the spirit of construction, because every layer is not just soil or aggregate, but the result of an engineer's hard work, discipline, and standard procedure. This is the philosophy of Civil Engineering Infrastructure (CEI), where site experience and knowledge together keep the true spirit of construction alive. Now that we understand the spirit of construction, let us see how this spirit takes shape in the first layer, subgrade. Subgrade, material and purpose. What is subgrade? Subgrade is the foundation layer of the entire pavement structure. It is constructed using natural soil or approved boro earth and is properly compacted so that the traffic load coming from above is uniformly transferred to the underlying soil strata. Material characteristics. Soil type. Generally clayey sand, silty clay, or murum soil is used. Highly plastic or organic soil is avoided. CBR, California Bearing Ratio. This defines the strength of the subgrade soil. Typical requirement, CBR greater than or equal to 8%. As per IRC 37, 2018. Moisture and density. Soil is compacted at optimum moisture content, OMC, to achieve maximum dry density, MDD. Ref. IS 2720 Part 7 and 8. Stabilized subgrade if required. Weak soil is improved using stabilization techniques. To enhance foundation performance. MoRTH and IRC references. MoRTH Clause 305, Earthwork for Embankment and Subgrade. IRC 37, 2018, Design of Flexible Pavements. IS 2720, Part 7 and 8, Determination of NDD and OMC. IRC SP 89, Guidelines for Soil Stabilization. Engineer's Note. Subgrade is not just ordinary soil. It is the soul of the road. If the foundation is properly compacted, the pavement strength automatically develops. Slide intent. This slide highlights that a road's strength does not lie on the surface, but in its engineered foundation preparation. A well-compacted and stable subgrade forms the base of pavement system reliability. Subgrade preparation. The true beginning of road construction starts here. Subgrade is the layer that carries the entire load of the pavement system. Therefore, its strength and uniformity are extremely important. Sequence of work. Clearing and grubbing. All bushes, roots, and debris are removed from the site, so that natural soil is properly exposed. Ref. MoRTH Clause 201. Setting of formation level. Formation level is fixed as per approved drawings and cross-sections, ensuring correct alignment and profile. Compaction of natural ground. Existing ground is compacted to 95% of NDD. Soft or weak soil is scarified and replaced. Ref. MoRTH Clause 305.2.2. Moisture Adjustment OMC. Moisture content is maintained at optimum moisture content OMC to ensure uniform and effective compaction. Engineer's Note. The compactness of the subgrade determines pavement life. If this layer is weak, all the layers above it become ineffective. Slide intent. This slide explains that a strong road always begins with a properly and uniformly compacted subgrade. Subgrade testing and reference codes. The quality of every pavement layer is proven through testing to ensure the strength and uniformity of the subgrade. The following tests are carried out as per prescribed standards. Main tests. As per IS and MoRTH specifications. 1. Field Density Test. IS 2720, Part 28. Sand Replacement Method Core Cutter Method. Purpose. To ensure required field compaction. Requirement. Field density greater than or equal to 95% of MDD. Reference. MoRTH Clause 305.2.2. 2. Moisture Content Test. IS 2720, Part 2. Oven Drying Method. Purpose. To verify optimum moisture content OMC during compaction. 3. CBR Test, California Bearing Ratio. IS 2720, Part 16. Field and Laboratory CBR Test. Purpose. To determine the load-bearing strength of subgrade. Minimum requirement. CBR greater than or equal to 8% as per project specification. 4. Plate load test if required. IRC 81, 1997. Subgrade evaluation. Purpose. To assess field deformation behavior of the prepared subgrade. Engineer's Note. Testing is not merely a process. It is the proof of trust and quality. Slide intent. This slide emphasizes that testing validates construction quality, and only a tested and approved subgrade can ensure long-term pavement performance. Subgrade field evaluation and approval. After subgrade preparation and testing, the next critical stage is field evaluation and approval. This is the stage where an engineer formally certifies the work. Evaluation parameters. 1. Field inspection. Visual inspection by IQA engineer. For surface uniformity, dryness, and camber. Any soft or yielding patches are identified and corrected before density testing. 2. Level and slope verification. Levels are checked using auto level or total station. Surface tolerance plus or minus 20 mm. Ref. MoRTH clause 305.4.2. 3. Compaction test review. Field density test IS 2720 part 28. Greater than or equal to 97% of MDD. CBR test greater than or equal to 8%. IRC 37/2018. If results are below criteria, recompaction is mandatory. 4. Moisture and surface condition. Moisture content within plus or minus 2% of OMC. No ponding of water or surface cracks permitted before the next layer. 5. Engineer's verification. Independent engineer, i.e., verifies all records. Field test logbook, density sheets, and level charts. After successful verification, subgrade approval memo is issued. MoRTH and IRC references. MoRTH clause 401.3 and 401.4 laying and surface tolerances. IRC 19/2015 guidelines for earthwork and granular layers. IRC 37/2018 design of flexible pavements. Engineer's note. Testing is not merely a process. It is the proof of trust and quality. Slide intent. This slide highlights that only a properly evaluated and approved subgrade forms the true foundation of a reliable pavement system. Granular Sub Base GSB, layer, material and purpose. Introduction. GSB, Granular Sub Base, is the first structural layer constructed above the subgrade. It provides the road with strength, stability, and drainage, and its proper material selection, gradation, and compaction directly determine the durability of the pavement. Purpose of GSB layer. Uniform load distribution. Evenly distributes the load coming from the subgrade, reducing stress concentration on the pavement system. Drainage layer. Allows rainwater or seepage to drain out, protecting the road from moisture-related damage. Working platform. Provides a smooth and stable base to support upper layers such as WMM or PQC. Protection layer. Protects the subgrade from erosion and frost damage. Materials. Crushed stone, crushed gravel, or coarse sand. Ref. MoRTH table 400:1. Plasticity index, pi less than or equal to 6. Liquid limit, less than or equal to 25. Los Angeles abrasion, La less than or equal to 40%. Deleterious material, less than or equal to 5%. Ref. MoRTH clause 401.2. Engineer's note. The GSB layer is the backbone of the pavement. It may not be visible, but the entire strength of the road depends on it. Slide intent. This slide explains that a road's durability is controlled not only by surface layers, but by a properly designed and compacted GSB layer beneath. GSB layer, field process and testing. Field construction process. Spreading. GSB material is spread and leveled to the approved thickness. Ref. MoRTH clause 401.4. Moisture conditioning. Required moisture is added to the material to ensure uniform and effective compaction. Compaction. Compaction is carried out using a vibratory roller with 80 to 100 kN static weight. Required density 98% of MDD. Modified Proctor test. Level checking. Surface tolerance plus or minus 10 mm. Layer thickness. Each layer less than or equal to 200 mm compacted thickness. Testing and quality control. Gradation test IS 2386 Part 1. Moisture content test IS 2720 Part 2. Field density test IS 2720 Part 28. Plate load test if required IRC 81 1997. CBR value for layer conformation greater than or equal to 30%. Engineer's note. Uniform compaction of the GSB layer determines the smoothness of the road, and testing alone proves its reliability. Slide intent. This slide highlights that controlled construction and proper testing are essential to achieve a stable and durable GSB layer. GSB laying and compaction process. Field execution steps. 1. Material spreading. Approved GSB material is spread to the required thickness using a motor grader. Loose thickness is kept within 200 mm. Ref. MoRTH clause 401.3. 2. Moisture conditioning OMC. Material is brought to optimum moisture content OMC to ensure uniform compaction. Test as per IS 2720 Part 2. 3. Rolling and compaction. Compaction is carried out using a vibratory roller with 80 to 100 kN static weight. Minimum 8 passes. 3 static plus 5 vibratory, or until surface movement stops. Rolling is carried out from edges towards the center. Ref. MoRTH clause 401.5. 4. Density conformation. Field density test IS 2720 Part 28 is conducted to verify compacted density. Required density greater than or equal to 98% of MDD. Modified Proctor test. 5. Surface level and finishing. Layer thickness and surface tolerance plus or minus 10 mm. Cross fall and camber are maintained as per approved drawings. Ref. MoRTH clause 401.6. MoRTH and IRC references. MoRTH clause 401 Granular Sub Base IRC 37 Design of flexible pavements. IRC 81 Subgrade and GSB field evaluation. Engineer's note. Smooth and evenly compacted GSB ensures road ride quality and proper bonding of upper layers. Roller sequence and OMC balance directly control pavement strength and durability. Slide intent. This slide highlights that GSB laying and compaction is not merely a process, but a combination of precision, testing, and engineer's judgment, which forms the foundation of long-term pavement performance. GSB material delivery and inspection. Material delivery and stacking. GSB material is brought from an approved quarry source. Ref. MoRTH clause 111 and 112. Gradation and moisture content are checked for each truck load. Before unloading, material is stacked on dry and clean ground to avoid any contamination. Coarse and fine fractions are stored separately to maintain uniformity. Oversized particles and excess fines are removed through visual inspection, quality inspection and approval. Source approval and quality certificates are verified by the engineer. Random sampling is carried out as per IS 2430, followed by sieve analysis as per IS 2386, Part 1. Gradation limits are confirmed as per MoRTH Table 400-1. CDR test may be conducted. For design confirmation, GSB material is allowed for site use only after approval. MoRTH and IRC references. MoRTH Clause 111 and 112, Source and Supply of Materials. MoRTH Clause 401, Granular Sub Base. IS 2386, Part 1 Sieve Analysis. IS 2430, Sampling of Aggregates. Engineer's Note. Approved source, proper stacking, and verified gradation. These three factors decide whether road durability begins from the base or ends there. Slide intent. This slide emphasizes that quality control starts at the material source, not at the construction stage. GSB spreading and level control. Spreading procedure. Approved GSB material is spread up to the formation level using a motor grader or paver. Loose thickness is kept within 200 mm so that compacted thickness remains uniform. Material spreading is continuously monitored. To avoid segregation, material is spread in slightly moist condition. For better compaction, Ref. MoRTH Clause 401.3. Edge and side slopes are maintained with uniform thickness. Level and surface control. Level checking is carried out using auto level or total station. Surface tolerance plus or minus 10 mm. Ref. MoRTH Clause 401.4. Cross slope and camber are verified as per approved drawings. Daily inspection logs are maintained by the engineer. Uneven areas are corrected before compaction. MoRTH and IRC references. MoRTH Clause 401.3 and 401.4, Laying and Surface Tolerances. IRC 19, 2015, Guidelines for Earthwork and Granular Layers. IRC 37, 2018, Design of Flexible Pavements. Engineer's Note. Proper GSB spreading and level control ensure road smoothness and effective drainage performance. Every leveling stroke reflects the engineer's responsibility on site. Slide intent. This slide highlights that accurate spreading and level control are essential for achieving a stable and durable GSB layer. GSB compaction and quality verification. Field compaction process. 1. Compaction equipment. Vibratory roller with 80 to 100 kN static weight. Minimum 8 to 10 passes. As per MoRTH Clause 401.4. Overlapping is ensured at edges. For uniform density. 2. Moisture adjustment, OMC. GSB is compacted at optimum moisture content, OMC. As per IS 2720 Part 8. Moisture is maintained uniformly throughout the layer. 3. Rolling sequence. Rolling starts from edges and moves towards the center. To prevent shoving, each pass is perpendicular to the previous one. For a uniform surface, rolling is stopped only after no visible movement is observed under the roller. 4. Density verification. Field density test, IS 2720 Part 28. Minimum density required, greater than or equal to 98% of NDD. Modified Proctor test. Density checks are conducted at random locations. Minimum 1 test per 500 square meters. MoRTH Clause 401.4, Rolling and Compaction. IS 2720, Part 2, 7, 8, 28 Soil Testing and Compaction. IRC 81, 1997, Field Evaluation of Subgrade and GSB. IRC 37, 2018, Flexible Pavement Design. Engineer's Note. Uniform compaction ensures road surface ride quality and durability. Every pass and every test is a part of engineering discipline. Slide intent. This slide emphasizes that proper compaction and verification are critical to achieving a long-lasting and reliable GSB layer. GSB level checking and final approval before WMM. Key field activities. 1. Surface level checking. GSB top level is verified using auto level or total station. Surface tolerance within plus or minus 10 mm. Ref. MoRTH Clause 401.4. Cross slope and camber are verified as per approved drawings. 2. Surface finish and cleanliness. Loose material or dust is removed using air jet or brush before approval. No water ponding or segregation is permitted. Defective areas are scarified and recompacted before acceptance. 3. Drainage and edge condition. Side drains and edge shoulders are properly shaped and compacted. GSB edges are sealed to prevent moisture ingress during WMM work. 4. Inspection and documentation. Joint inspection by the engineer and concessionaire's QA team. Level charts and density records are submitted for approval. Written clearance is issued by the engineer before WMM laying. MoRTH and IRC references. MoRTH Clause 401.4, Surface Tolerances for GSB. IRC 192, 2006, Construction and Quality Control for Granular Layers. IRC 37, 2018, Design of Flexible Pavements. Engineer's Note. Level accuracy and surface cleanliness determine the ride quality and bonding strength of the next layer. Engineer's approval before WMM is the final assurance of road quality. Slide intent. This slide highlights that final approval of GSB is a critical checkpoint before WMM construction and ensures long-term pavement performance. Wet mix Macadam WMM layer material and purpose. Purpose of WMM layer. Uniform load distribution. The WMM layer distributes the load uniformly between the subgrade and GSB, thereby enhancing the overall strength and durability of the pavement system. High strength and stability. Mechanically mixed aggregates form a dense and interlocked layer that provides high road stiffness and resists traffic-induced deformation. Drainage layer. Well-graded WMM helps in moisture retention control and assists in effective seepage management. Working platform. Provides a smooth and stable surface to support bituminous layers, DBM-BC. Material requirements. 1. Aggregates. Crushed stone, clean, angular, and durable. Gradation as per MoRTH Table 400-10, Clause 406. Maximum size. 53 mm for upper WMM. 75 mm for lower WMM. Los Angeles abrasion value, less than or equal to 40%. Flakiness index less than or equal to 15%. 2. Binder material. Quarry dust or screenings, pi less than or equal to 6. To achieve proper aggregate interlock. Free from clay or organic matter. 3. Water. Potable or clean water, free from impurities. Used at optimum moisture content, OMC. During mechanical mixing. Engineers note. The real strength of WMM lies not just in the mix, but in its uniformity, correct moisture content and gradation of every aggregate particle form the true base strength of the road. Slide intent. This slide explains that WMM performance depends on material quality, gradation, and moisture control, which together define the structural reliability of the pavement. Wet mix Macadam WMM, field process and testing. Field construction process. 1. Material mixing. Aggregates and water are mixed in a mechanical mixing plant at optimum moisture content, OMC. Mixing is continued until each aggregate particle is uniformly coated with fines. Ref. MoRTH Clause 406.3. 2. Transportation. Mixed material is transported to the site using tippers. Spreading should start immediately after unloading to prevent moisture loss. 3. Spreading. Material is spread using a paver finisher or motor grader to an approved thickness, less than or equal to 200 mm compacted. Cross slope and camber are maintained as per approved drawings. Ref. MoRTH Clause 406.4. 4. Compaction. Compaction is carried out using a vibratory roller with 80 to 100 kN static weight. Minimum 8 to 10 passes are required until no visible surface movement is observed. Uniform density is achieved across the entire width. Ref. MoRTH Clause 406.5. 5. Surface finish. Surface should be smooth and free from segregation. Any cracks or loose zones are scarified and recompacted. Engineers note. The compacted WMM surface is the load transfer key of the road. If density and OMC are properly controlled, the pavement strength develops automatically. Slide intent. This slide highlights that controlled execution and strict testing are essential to achieve a strong, uniform, and durable WMM layer. Wet mix Macadam WMM laying and compaction process. Laying process. 1. Surface preparation. Ensure the GSB layer is clean, dry, and approved before starting WMM work. Surface is lightly sprinkled with water to avoid absorption of moisture from WMM mix. Ref. MoRTH Clause 406.4.1. 2. Spreading. WMM material is unloaded from tippers and spread using a paver finisher or motor grader. Spreading thickness before compaction. 225 to 250 mm to achieve 200 mm compacted thickness. Longitudinal joints are staggered between successive layers. Ref. MoRTH Clause 406.4.2. 3. Cross fall and camber. Maintained as per design cross section. Checked using auto level or template after spreading. 4. Moisture control. Optimum moisture content, OMC, is maintained during spreading and compaction. Water is resprayed if evaporation occurs due to heat or wind. Compaction process. 1. Rolling pattern. Rolling begins from the edges and proceeds towards the center. Vibratory roller. 80 to 100 kN static weight. Is used for compaction. Minimum 8 to 10 passes. Until no visible surface movement is observed. Ref. MoRTH Clause 406.5.1. 2. Edge compaction. Edge areas are compacted separately to ensure proper bonding and avoid edge failures. 3. Density requirement. Minimum field density greater than or equal to 98% of NDD. Modified Proctor test. Tested as per IS 2720 Part 8 and 28. 4. Rolling sequence. Rolling is carried out in alternate directions at right angles to ensure uniformity. Final passes are done with the roller in static mode. Engineer's note. Precision in WMM laying and compaction directly controls the life of the road. Every pass and every reading carries the engineer's responsibility and signature. Slide intent. This slide emphasizes that controlled laying, correct roller sequence, and density verification are critical for achieving a durable and long-lasting WMM layer. Wet mix Macadam WMM field testing and IE approval. Field testing. Field density test, IS 2720 Part 28. Minimum 1 test per 250 square meters area. Required compaction, greater than or equal to 98% of NDD. Modified Proctor test. Moisture content test, IS 2720 Part 2. Moisture variation within plus or minus 2% of optimum moisture content, OMC. Ensures uniform compaction. Gradation test, IS 2386 Part 1. Random sampling from laid material to confirm compliance with MoRTH Table 400 to 10. Thickness check. Verified by level readings or by measuring depth at cut points. Compacted thickness greater than or equal to 200 mm. Surface level and cross fall. Checked using auto level or total station. Tolerance plus or minus 10 mm. Ref. MoRTH Clause 406.5.2. Documentation and approval flow. 1. Field test results compilation. All test results, density, moisture, gradation, are compiled by the site QC engineer. 2. Submission to IE. Reports, level charts, and field registers are submitted for review. 3. Inspection and verification. Independent engineer, IE, verifies test data and conducts joint site inspection. 4. Approval or NCR. If all results meet specifications. Layer approved for DBN. If deviation is observed. NCR, non-conformance report. Issued for corrective action. Engineer's note. Testing and approval are not merely formal processes. They represent the engineer's responsibility and trust. If WMM is properly compacted, the bituminous layers above can perform for decades. Slide intent. This slide emphasizes that proper testing, documentation, and IE approval are essential checkpoints before moving to bituminous construction. WMM level checking and final approval before DBN. Surface checking and verification. 1. Level and cross slope verification. Verified using auto level total station. Tolerance plus or minus 10 mm. Ref. MoRTH Clause 406.5.2. Camber and longitudinal profile. Checked at every 25 meters. 2. Surface cleanliness and condition. Loose particles, dust, or segregated zones are removed using air blower or brush. No standing water or rut formation is allowed. 3. Edge compaction and drainage. Side edges are well compacted and sealed. Temporary side drains are opened to protect the layer from rainwater. Approval procedure. 1. Joint inspection. Conducted by independent engineer IE and concessionaire's QA team. Surface profile, density, and gradation reports are reviewed. 2. Test reports submission. Field density test, IS 2720, Part 28. Moisture content test, IS 2720, Part 2. Gradation test, IS 2386, Part 1. Level chart, MoRTH Clause 406. 3. Final approval. If all parameters are satisfactory. WMM layer approved for DBM laying. If deviation is found. NCR issued and corrective action recorded. MoRTH and IRC references. MoRTH Clause 406.5 and 406.6 Surface Tolerance and Quality Control. MoRTH Clause 900 Quality Assurance. IRC 37, 2018 Flexible Pavement Design. IS 2720, Part 2, 28 Field Density and Moisture Tests. IS 2386, Part 1 Gradation Test. Engineer's Note. After final approval, the road base is officially declared ready. The engineer's signature becomes the guarantee of durability, proved by every passing traffic load. Slide intent. This slide confirms that final approval of WMM is the last technical checkpoint before starting DBM laying. Next, Part 3, Bituminous Layer Construction, DBM and BC. Transition message. So far, we have clearly understood the construction of Subgrade, GSB, and WMM layers, which together form the foundation of the road. Now comes the stage where strength, bonding, and smoothness come together. Bituminous construction. What comes next? 1. Prime coat and tack coat application. Bituminous coating required for proper bonding between WMM and DBM. 2. DBM dense bituminous macadam. The structural bituminous layer responsible for the load-bearing capacity of the pavement. 3. BC bituminous concrete. The final riding surface of the road. Smooth, waterproof, and durable. 4. Quality testing and field control. Temperature checks during laying. Core extraction and binder content testing to ensure long-term pavement performance. Engineer's note. The base layer gives the road its foundation, but the bituminous layer gives it identity. This is where strength and smoothness meet, and the road truly comes to life. Slide intent. This slide prepares the viewer for the transition from base layers to bituminous construction, highlighting the importance of bonding, structural strength, and ride quality. Jai Shree Ram. You are watching Civil Engineering Infrastructure (CEI), a platform dedicated to road construction, concession agreements, and practical knowledge on QA/QC. At CEI, we believe in delivering practical knowledge from field to classroom, because every engineer deserves the opportunity to learn and grow. If you find our content useful, watch our videos and subscribe to our YouTube channel. And don't forget to press the bell icon to stay updated with our upcoming videos. You can also connect with us on social media platforms and stay regularly updated through Instagram, Facebook, and LinkedIn. under the Civiling Infra handle. And always remember, knowledge is power only when shared. See you in the next part, where we continue the journey of learning and construction. Jai Shri Ram.